Okay, so everything's recorded. All right, cool. So let's go ahead and erase this. Okay. We'll go ahead and move on to the final material pertaining to this these sections, and this would be everything pertaining to the homework that's due tonight. So the even and odd function. So normally even and odd is really easy to determine if you're given a graph, because it's simply, is it symmetric about the y-axis? Do you see symmetry there? Is it symmetric if you rotate everything 180 degrees? Or is it just a big mess and there's no symmetry? But what about if you're given a function and no graph? Now, throughout these sections, we are comparing the functions and graphs. Graphs are visualizations of functions. So what about if we don't have a nice graph to look at? Well, this is when we determine even and odd algebraically. And I did mention above in this section how to do it algebraically. The function is even, and then I put this information here. Kind of looks a little messy, that's fair. And I'll explain what that means in a second. It's odd, and then I put some other stuff. There's a bunch of negative signs all over. What does that all mean exactly? And so that's what I'm going to explain below. So for example 2 here, determine algebraically whether each one is even, odd, or neither. So I noticed a lot of you got these right on the homework because they're multiple choice. And I know how that goes. You clicked, clicked. I would have probably done the same thing. So let's explain why it's actually the choice that you picked that ended up being right over process of elimination. So we'll start off with example 1 here. Determine whether this thing is even, odd, or neither. So we'll start off with even. And so the process here for even is to replace every x you see with a negative x. So what's the function we are referencing? So I'm going to write it down again. So I see a -2, but hey, I see an x. So guess what? I replace that x, and I use parentheses, a negative x. So notice, and that parenthesis is important. It's good to do that anytime you replace or substitute anything. Minus 9, and I see another x. So guess what? I put a negative x in its place. So that was the first step. I replaced every x I saw with a negative x. And now I'm going to simplify. So the question is, well, for that -2 times negative x to the third, that negative x to the third, in other words, what happens to the negative on the x? Does it go away? It does stay, because a negative value raised to the third power, well, you can think about it as -1 times -1 times -1, which is -1. So that negative sign that's next to the x stays. And more so, it stays in the sense that it does not terminate. So that negative gets to come to the front. But there's already a negative out there because of the -2. Like naturally, you see where this goes. Those negatives cancel. So that's why this term becomes 2x to the third. That should be a 2. So that first term, those 2 negative signs cancel out. That negative in the power of 3 doesn't cancel out, so it comes to the front and cancels out with the negative that was already in the front. It's the same idea for the -9 of negative x, or -9 times negative x. You have a question? What's that? Why does the 2 go there? Oh, the 3? Because the 3 is still raised to the x. So the 3 is being raised to the negative sign and to the x. We took care of the negative sign and it got to go to the front, but it's still stuck on that x. Yeah, so that's why. So, and with the next term, well, it's technically the same idea. We have negative x to the first power, which might seem a little trivial, but in any case, that negative does not terminate. Normally that termination happens if we have an even exponent, like a 2 or a 4. So that negative comes to the front, where there's already a negative in the front of the 9, that is. So -9 times negative x plus 9x. All right, so we replaced every x with a negative x. We simplified. The final step is that simplified form equal to the original function in the problem. So the -2x to the third minus 9x that we started off with in the very beginning. Are those the same thing? No, because, well, one's got negatives. This one has a bunch of positives. So it's not even. It's not even because we did not get the original function back, the one that we started off with in the very beginning. If we got that exact function back, letter for letter, sign for sign, everything, then we would say it was even. I'm not going to end up doing problem 3. I'm going to just skip ahead. 3 is even. So that might be something you might want to check on your own. But let's check odd, because remember, there's odd. So we found out it's not even. But if you may remember from your homework, there's 3 choices. One was even, evens out. There's odd, and then there's neither. So naturally, we need to check odd. So odd only takes us one step further. It says multiply what you found in the previous part. So this is why even is good to do first. Odd says take what you finished with. So the 2x to the third plus 9x that we found in the even step. So that's exactly what we found in the even step. And then just multiply it by -1. And then the question is, does that simplified form give you the original function? It's basically, Dret, that didn't work for even. All right, try this. Yes?
So what happens if you do odd first? And then go
Well, if you do odd first, you would have to do both of these steps at once. If even, well, so that's kind of the reason why even is good to do, because you can recycle the leftover from even and apply it to the odd situation. But with odd, you would have to replace all the x's with negative x's, and then you would have to multiply that whole expression by -1. And then if that didn't work for even, you would have to multiply everything by another -1. So that's a lot more steps. So it's good to check even, and then odd, and then neither, in that order. Gives you the least amount of work. So here, it's the same idea. It's pretty much the same thing as flipping all the signs. If you have a fraction, it's not necessarily true. But we're multiplying this by -1. Oops. Did I mention I can't wait for that new computer? Did I mention that? Okay, so multiplying everything by -1. So it's going to flip every sign, in essence. So those pluses, those positive terms become negative terms. And now we ask, now are we back at the original function from the very beginning of the problem? Yes, we are. So check. It's odd. Okay, so that is odd. And then if it failed both of those conditions, it would be neither. So problem 2 here, those bars around the -2x, those are absolute value bars. You might or might not be familiar with them from high school. If not, the bars mean take any number inside of it. And I mean, this is kind of stretching a little bit, but it ultimately turns everything positive. So technically, I could take that negative out from the -2x. But I'm not going to focus on the algebra of an absolute value so far. I'm just going to look at, I'm just going to start off with even. So what even says, place every x with a -x, like we did before. I replaced every x with a -x, and I kept everything else the exact same. Every -x, I put parentheses around to really emphasize that substitution. And then you simplify it. So -9 times -x is positive 9x. And then plus, and I see those bars, -2 times -x just so happens to become positive 2x. So we ask ourselves, is that simplified form equal to the original function from the beginning of the problem? Now, it's got a 9x. The original problem had a -9x. That already throws it off. So let's keep going. For odd, we have that. All right, there we go. So here, eraser, that. Okay, so it's not even. It's not even. I'll pretty much characterize that by just, so it's not even. Let's try odd. So it says, so odd says, take that original result that you got from the end of even. So at the end of even, we found exactly 9x plus absolute value of 2x. And multiply all of the numerator terms, or multiply the whole thing by -1, like we did before. So we're multiplying that whole expression by -1. I guess to sort of emphasize that, it would be this. And so the question is, does that give us the original function from the beginning of the problem? No, it does not. The original function had a plus sign here. Our final answer does not have a plus sign there. It has a minus sign there. That's a big deal. It means it's not odd. Not odd makes it neither. That's why those choices that you spammed into my math lab actually correspond to whatever the correct answers were by using this process. And then for problem 3, well, definitely convenient because I don't have any room. That is something you can go ahead and confirm on your own. You will anyway, because that is a homework question. So hopefully you go in and convince yourself why that is even. So let's see if someone asks me the question that I get asked every semester. About a certain pattern you may see. Yes?
Is that exponents are odd?
Yes, so the natural question of is odd, even, and neither corresponding to the exponents? Because you may notice in problem 1, the exponents are 3 and 1. Those are odd numbers. Notice we got odd. Problem 2, well, absolute value is even, in essence. Might be weird to see. It's a little bit weird when you have funky symbolism, and then it has a absolute value would be even. 9x, that has a power of 1, which is odd. So a mixed match would mean neither. Problem 3, that would be even because you see an even exponent. There's only, if you want to use that style, that pattern, then there's only one thing I would want you to try to figure out in your own mind. Is that even, odd, or neither?
No.
It is neither. A lot of people naturally say that that problem is odd because they see the odd exponents. However, that's an even term. Just sort of a counterexample that I've seen in my years of teaching this class. But for the most part, the exponents do give you a pretty good rule of thumb. So hopefully that helps. So in-class people, anything else? Let me move on to my Google Meet people. I cannot wait to get that new monitor. Okay, so let me go ahead and erase this. Erase. Again, with the new monitor, I can write smaller and I don't have to erase. It just sticks with the page I'm working on. Very cool. So the last thing for this section, and this is probably for the majority of you, I am proud that most of you went through and answered all the questions that pertain to the problems we did work on. And for most of you, you were sending me emails about what to do with the local stuff, and I told you to skip it for now. We'll talk about it Monday. But I think it's very tame. There's really not much you have to do with it. And I'll show you why. So a local minimum or maximum, so a local minimum is just the lowest point of any cup shape behavior. So we call it the lowest point in a valley. So as you can tell in example 3, there's 3 of those. There's 3 kind of cup shapes, ultimate arcs, and the lowest points are filled in circles. Those would be local minimums, plural. An absolute minimum would just be the lowest one. As you can tell, the quantity is prefaced by the namesake of the terminology. Local implies more than one. Absolute implies a singularity. The maximum stuff, very similar, but it's the peak of a hill. So peak of a hill. Local means that there's more than one. Absolute just means what's the highest. And to sort of convince you all of the brevity of these sorts of problems, why you should be able to finish these, and very minimal amount of time, rather. Let's go ahead and look at example 3. And they give us this graph and ask us to find some things about it. Start off with finding, for part A, it says find the x values of the local minimums, or all the places where a local minimum exists. So local minimum, local means more than one. Minimum means all of these low points of every valley. There's 3 of them. And I just went ahead and illustrated them there. So it wants to know the x values. So, okay, fine. You find the x values of each one of those points. So for that first one, it's -10. The second one, it's -2. And the third one, it's 3. Just the x values. They're specifying we want the x values. So you would put -10, comma, -2, comma, 3. No ordered pairs, just a list. Those would be the local minimums. Now, conversely, part B wants you to find the local maximums. So naturally, it's all the peaks. So it's all the peaks, and then it wants the x values. So that would be -4 and 0. And then part C may look tricky. I'll just write up the notation because I kind of write a little large. It wants to know the absolute minimum. Absolute meaning 1. Minimum meaning, well, bottom of a valley, lowest point of a valley. So if we look at this whole thing, we found 3 minimums, and then we just picked the one that's the lowest. Gone, gone. This one's the lowest. And so this fancy notation that they are using means in the parentheses, that's where the x value goes. And then what it's equal to, that's the y value. The y value seems to be -7. And that's it. That's local minimum, local maximum in a nutshell. So those problems you should be able to knock out fairly quickly. It's just identification, no intervals or anything like that. Cool? Good. Google Meet people. Okay. Let's go ahead and move on. So this concludes everything for this homework set, these 3 sections in particular. That homework, like I said, is due tonight. So I cannot push back any homework assignment without a doctor's excuse. So if you ask me, I'll have to say no. So tonight's the homework for that in my math lab. Tomorrow is the quiz. Let's go ahead and move on to something that may be more familiar. Lines and linear functions. I guarantee that half of this section is probably stuff you've seen before, and if so, great. Go ahead and utilize that. I have this homework due Thursday. I'm not going to be able to go through all of it today, but I will finish this section on Wednesday, no doubt. So lines and linear functions. So throughout this chapter, in essence, what we're doing is we're taking a function, which is a collection of numbers and variables, and we compare that to some graphical representation, something that helps us see the inner mechanism of everything going on. A line is a geometric representation of a linear function. Normally in high school, you think of linear as line. The reason why this association is so profound is because one is this visual interpretation of the other. But that's more so conceptual. So we're dealing with lines, tons of lines. And we'll start off with the most simplistic characteristic of lines, slope. You're probably all familiar with slope. You might all be familiar with y2 minus y1 over x2 minus x1. If not, here it is. And it's equivalently known as rise over run. I will use both of these versions in example 1 here. And then I'll explain this little detail after I do example 1. So let's see. Maybe I can keep everything on the screen here. So let's go ahead and do example 1. So it just says, find the slope. And it also says interpret the slope, which I'm just going to verbally explain what a slope is. A slope tells you how sharp or dull the incline or decline of a line is. A large positive slope would mean, so a large positive slope would be a very sharp incline. A small positive slope would be a very small incline, just like that. And we have some algebraic ways of determining that using the y2 minus y1 over x2 minus x1, the rise over run stuff. So if we find the slope, and as you can see, we are given 2 points, we can find the slope in one of 2 ways. We can use, well, y2 minus y1, all that stuff, or rise over run. I'll use the y2 thing first and then the rise over run second. This may be familiar stuff. If so, this might be a breeze. So if we use y2 minus y1, and obviously we need to know what all this stuff means. And what this does is it's saying what's the first x value, what's the first y value, what's the second x value, what's the second y value. So what we can do is just label them somewhat arbitrarily. It doesn't even matter. So that point on the left could be x1, y1. It's the first x value and the first y value I'm identifying. And then same thing with the other one. It's the second x value and the second y value. That's what that notation means. So naturally, when I go and plug this into the formula, all I'm doing is swapping out variables with numbers. y2, come all the way down here and see that y2 is -4. y1 seems to be 2. x2 is 3 and minus -1. There's minus signs in the formula already, so we do have to keep those, whether the value is negative or positive. And we have to add another negative if the value has a negative sign already, like that minus -1 down here. But from there, it's just a matter of simplifying. -4 minus 2 is -6. 3 minus -1 is 4. And that's a fraction we can pretty easily simplify as -3 over 2. So this is the slope, which we normally use the variable or the letter m to identify that. Why is it m? Most likely it's a German word. We tend to steal a lot in math and science from the Germans. Or it could be something else, I don't know. That's what I assume. So that would be one approach. That would be the more so algebraic approach. let's say if we didn't have a graph. But you might think, well, Brad, we do have a graph. And I agree, we do have a graph. So what would be the equivalent graphical representation of finding the slope? If you're given a line, how do you find the slope? Well, that's when we utilize rise over run. And I'll use two colors to represent this, but rise, naturally, that is a vertical shift. So from the left, oh, you have a question?
So if there's not a graph, you use rise over run?
If there's not a graph, you use the y2 minus y1 stuff.
Okay.
Yeah, naturally, because rise over run are visual properties, and having a graph is a visual thing. So you can think about it in that way. You can't rise or run if you don't have a graph for which you have no spatial understanding of. And there's more examples later on. We'll see in more detail what's appropriate to use in which situations. So let's see. So I have red here. So since we do have a graph, we can use rise over run because we do have a concept of rise, which we would rise all the way to that other point that we are given. So notice I went downwards. Let's draw that again. I go downwards as much as it takes to get to the other point. So this would be the rise. So it's a negative direction. We're going downwards. We can rise downwards. I know it's kind of weird. It would be a negative rise. So how many units did we go down? We can count them. 1, 2, 3, 4, 5, 6. We go down 6 units. So it's -6. This may already seem familiar to our other example. And in blue, I'll just specify run right quick. So run would be distance. Of course, we run horizontally. So that blue line, that would be the run. How many units was that? 1, 2, 3, 4. So 4. And these numbers, again, may look familiar, as they should. This is the complete geometric representation. So naturally, rise over run. The rise was -6, the run is 4. And then we simplify that as -3/2. It's the same exact problem, just a different way to set it up. Does anyone have any questions about this? This may be review, and if so, that's good for you. It'll just be a little bit easier for you to follow along. If not, then this is kind of a basic understanding of the implementation of various slope formulas. Okay. So before I move on, I did want to mention this little excerpt I have right here. So a problem with having a fraction like this, a natural problem with fractions in general, is the issue of having 0 in the denominator. It's normally a pretty bad thing. It's kind of lame. And how do you get 0 in the denominator of this fraction? Well, if your x's are equal, is x2 minus x1. Well, let's say they were both 3, and 3 minus 3 would be 0. And then you have a 0 in the denominator, which is lame. So what happens in that case? Why is that lame? Well, lame is a colloquial replacement of the more refined word, well, undefined. So 0 in the denominator leads to something that is undefined, which translates to a vertical line. Vertical line. If you missed that, it's written right here. Vertical line, slope is undefined in the notes right there. So they are complete associations. They work in tandem. So vertical line means undefined slope. Undefined slope means vertical line. Now, so that was if the x values are equal. If the y values are equal, then the 0 is in the numerator. And that's okay. You can have the 0 in the numerator. And if that happens, then you get a horizontal line. So horizontal line, and the slope is 0. So horizontal line has a slope of 0 because you're not rising at all. If you did, then the line wouldn't be flat on the ground. So that'll help you answer a few homework questions right there. And we have a problem coming up that actually talk a little bit about that in relation to a certain equation. Okay, so talked about that. Let's not do that. There we go. Okay, so let's go ahead and move on to slope-intercept form. So there's really 3 forms used to identify a line. One of them, which is general form, we will not talk about at all. Found a way to just get around it entirely. So we're going to talk about, we'll start off talking about the most important one, slope-intercept form. Y is equal to mx plus b. This may be the most familiar to everyone in here. Y is equal to mx plus b. And it's defined here, just in case you missed it. And in this characterization, m represents the slope, and b represents the y-intercept. So why is it called the slope-intercept form? Because it's a form that you can build if you have the slope and the intercept. So the namesake is not arbitrary here. It's called slope-intercept form because you use it when you have a slope and a y-intercept. And we'll talk about how to construct that in these coming problems. Now, if you have a vertical line, we talked about vertical lines having an undefined slope. So obviously, you cannot get a slope. So what do? You have a vertical line, you cannot use slope-intercept form because there's no slope. So they kind of give it to you for free. Then the equation is simply x is equal to a. And what is a? A is the x value. Again, I have a problem coming up that talks about this. You might notice that example or part 2 here. I'll talk about what to do, but just keep that in mind that a vertical line, since there's no slope, it will not be written as mx plus b for vertical lines only. So let's go ahead. Maybe I can. Maybe can you all in-class people? Can you all see that just fine? Okay, cool. So I can show the formula and the graphs and stuff. Cool. So graph the line having a point and a slope, and then determine the equation. All right. So example 1 here. They give us a point and a slope. So let's go ahead and plot the point, because that's pretty easy. The point is -2, -3. Go to the left 2 and down 3. Two, 3. And so there's the point. And now it says that the slope is 3. So how do we use that to our advantage? Well, I want to emphasize that 3 is equal to, wait for it, 3 over 1. And that should be a 1 and not a 7 or what. That's 3 over 1. And you might think, okay, all right, we get it. You're good at math. You put it over 1. Why'd you do that? Who cares? And so the reason why that matters is because the reason I forced it to be a fraction is because now we can equate it to rise over run. So now we have a rise. Let's see if I can fit that here. So now that's rise over run. That says rise over run. So now we know from the point that we just plotted, we rise 3, which means we go up 3. So 1, 2, 3, 3, and we go to the right once. Right there. And on your end, when you do this in your homework, it will, when you plot the 2 points, it will sketch the line for you. So you don't have to do anything wonky or anything. You plot the 2 points, it will graph and construct the line for you. I will not be as perfect here. So let's try and, okay. Wasn't as bad as my last class. Okay, good enough. So on your end, you will see a perfect line. And the reason why I emphasize why that line being perfect is a helpful thing is because you can figure out some characteristics that help you build the equation. Because this problem wants you to determine the slope-intercept form of the line. Well, how do you figure out the slope-intercept form? You need the slope. Okay, they gave us the slope for free. And you need the y-intercept, which now that we have the graph, we can just look. So this is, so remember, this is y is equal to mx plus b. That's the slope-intercept form. The slope they gave us was 3. And the y-intercept, remember the y-intercept, we talked about this before. It's where the graph intersects the y-axis, which I just illustrated in red there. What's the y value? It's 3. And that would be the slope-intercept form of the line. That's it. So having a graph is pretty helpful. You just look at it. Now, problem 2 here, it gives us a point, and then it says that the slope is undefined. All right, well, if anything, let's plot the point. So that seems to be right there. So I plotted the point, 4, 3, and it says that the slope is undefined. What does that tell us about the line? So it's vertical. That's what it means for a slope to be undefined, vertical. So this implies vertical. It implies vertical. So we don't even have to find a second point. We just draw a vertical line. And then on your end in my math lab, all you have to do is just plot, because it'll want 2 points. 1 point's easy. Second point, you can just plot anything you want, as long as you get a vertical line. So anything relative to, you get a vertical line. And so it says determine the slope-intercept form of this. Well, we don't have a slope. So we have to use that equivalent form. And again, I wrote that up here. It says x is equal to a. So how we translate that is x is equal to the x value, which is 4. And that would be it. So it does not conform to it does not have a y is equal to mx plus b thing. It just, vertical lines have their own thing. It sucks that there's another exception, but the exception is at least simplified. Just one little thing you have to find. So that would answer problems of those caliber, of that caliber. In-class people, how do you feel about that? Is it cool? Not cool? Like neat people. Okay. So let's go ahead and move on to whatever we're moving on to. Probably x and y intercepts. Maybe point slope. Oh, yep, point slope. Okay, so we're going to move on to point slope, which is another form for a line. Now, in essence, it's normally not a simplified form. Normally we use this form, we simplify it, and then we get point slope intercept form, which I'll explain in example 3 here. But normally point slope form is something we start off with, we simplify it, and then we get the previous equation, the mx plus b. So it's kind of a stepping stone, in essence, as example 3 will show us. So here's another equation, though. So here's another equation, and you use this equation when you have a point and a slope, hence why it's called point slope. And so, yeah, so that's when you use this formula, if you are given a point and you have a slope. So example 3, well, we need a point and a slope. Example 3 gives us a slope and a point. Oh, wait a minute, that's the same thing. So for example 3, they give us a slope and a point, which means we can use point slope form. So what this information tells us, they give us that the slope is -3, and the point so in other words, the x1 and the y1 from the above formula. So notice there's an x1 here and a y1 there. That's where the x1 and y1 come from. It comes from the point. So we just plug in everything. So the formula is y minus y1. I'll just write it out just to be very explicit. The y1 is just +1. There's already a minus sign in the formula, so I have to keep the minus sign. The slope is -3. X has to stay because it's a variable, minus x1, where x1 is -2. There may be 1 or 2 problems that ask you to leave your answer in point slope form, just that form alone, which this would be it. This would already be point slope form. But naturally, we want to take this information and rewrite it in slope intercept form. That's mainly the most important formula in this section, slope intercept form. So we're going to continue from this form, and I'll go ahead and clean it up slightly. There was an x minus -2, which I just made +2. And now it's nice and cleaned up to where we see that distribution would be the next step. We distribute. So finally, one stipulation about, so this is not in slope intercept form. One of the characteristics of slope intercept form, y has to be by itself on one side of the equation. Obviously, y is not by itself. There's that -1 in the way. So naturally, we use a little bit of algebra, add 1 on both sides. So add 1, add 1. Y is equal to -3x minus 5. So that should be a y. And this would be the answer for the slope intercept. So that would be the slope intercept form. So generally, we use point slope form as a way to set up a pretty much an initial structure of the formula. And then generally what we do is we work it out, do a distribution here, like terms there, we get the final answer. Does anyone have any questions up to this point? If not, let's go ahead and move on to x and y intercepts. And we've already talked about x and y intercepts before. Now we're going to look at them from an algebraic perspective. Because naturally, we take these geometric representations and view them algebraically. So we've talked about intercepts before. We have two of them, an x-intercept and a y-intercept. I even wrote down here what the geometric interpretation is. When the graph intersects the x-axis, that's an x-intercept. And similarly with the y-intercept. So that's all there to just remind you. But what about if you don't have a graph available? So how do you find them if you have a function and not a graph? Well, I went ahead and gave the process for doing that. If you have a function instead, the x-intercept can be found, set y equal to 0 and solve for x. That's how you find the x-intercept. Set y equal to 0. We'll see that in example 4 here. And you solve for x. The y-intercept, you set x equal to 0 and solve for y. And doing this general process, you're going to see this more than once. You're going to see it a lot of times. So you might as well highlight this. You might as well asterisk it, star, whatever. You're going to be finding the x and y intercepts for the remainder of this class. It keeps coming up. But this is how you do it. So you set x equal to 0, solve for y to get the y-intercept, or you set y equal to 0 and solve for x to get the x-intercept. So probably the most simplistic example of this, let's look at example 4 here. So they gave us this equation, and the first part A, they want us to figure out the x and y intercepts. So to find the x-intercept, so what was the rule? It's set y equal to 0. There we go. Set y equal to 0. And we're going to solve for x. So we have this equation up here. So now there is a y that we can set equal to 0. So it's 2x plus 3, but not y, because y is now 0. Six, so that should be a 6. Well, that's convenient because 3 times 0 is 0, and it simplifies to 2x is equal to 6. And just one more step. X is equal to 3. So that would be the value as So my math lab will sometimes go back and forth between asking for the number and the ordered pair. This would be the number, and the ordered pair would be 3, 0. And that makes sense because we set y equal to 0 to facilitate all of this. So this is how you find the x-intercept. And the y-intercept is very similar. The y-intercept, you set x equal to 0. So it's going to be very similar. I'll replace x with 0. Solve for y, which ends up being 2. The ordered pair would be 0, 2. And the reason 0 goes first here is because the x always goes first, and we set x equal to 0. So that's how you find the x and the y-intercept. This process will come up again and again in this class, so I'm really trying to emphasize it here. Let's go ahead and graph the equation. So in my math lab, as I mentioned, it will graph a line for you if you give it 2 points. It will sketch a line for you. If only we had 2 points. Oh wait, we do have 2 points. The x-intercept and the y-intercept. So naturally, the x-intercept is 3, 0. And the y-intercept, 0, 2, right here. By plotting those 2 points, it will sketch the line for you. Which is normally helpful for determining things like the, slope, perhaps, if you don't have it already. So part C, I'll go ahead and just put that up over here. Part C wants us to find the slope-intercept form. Well, slope-intercept form, let's remind ourselves, that's y is equal to mx plus b. Don't I know how to try it again. Mx plus b. So in order to determine the slope-intercept form, we need 2 things. We need the slope and the y-intercept. Well, the problem doesn't give us the slope anywhere. So that means we got to go find it. We have a graph. So how do we find the slope given a graph? We use rise over run because we have a graph. So we can use rise over run. So in blue, that's the rise, which seems to be -2. The run seems to be +3. And so the slope, I'll put it over here. The slope would be -2/3. It's rise over run. So if anything, we can start to fill in our formula. So y is equal to -2/3x, because -2/3 is the slope. Now we need the y-intercept. How do we figure out the y-intercept? Like, we already did figure out the y-intercept. We did it in part A. What was the y-intercept we found? It was 2. So the y-intercept is 2. We found it right here. We found it already. So it's 2. You can also just look at the graph as well to confirm that if you want, but this would be the slope-intercept form. Does anyone have any questions about any of this thus far? Cool. So hopefully this is review for the majority of you. If you haven't been in school a while, this might be a nice refresher. Let's see. So we go ahead and erase. So I wanted to finish parallel stuff. So I'm going to do example 5 and we'll call it a day. So to lead up to that, so parallel and perpendicular lines. So I'm going to focus on parallel today, and I'll start up with perpendicular on Wednesday. So we all have some sort of fundamental idea of what parallel lines are. Just 2 straight lines, they go on forever, never intersect. That's parallel. Normally we normally compare that to train tracks. Just go on forever, never intersect. So, but naturally, we like to take geometric interpretations of things and try to figure out their algebraic counterparts. If you don't have, in other words, if you don't have a graph, then how do you determine if 2 lines are parallel or not? Just given just two functions of lines or 2 equations of lines. And I wrote that here. They have to have the same slope. 2 lines are parallel if they have the same slope. So that's it. That's the criteria. So if they have the same slope, it doesn't matter what else is the case. If they have the same slope, they will be parallel. And that makes sense because slope tells us the steepness of the line and the direction, whether it's an incline or a decline. If they both incline at the same amount, then naturally they will be parallel. So this makes sense intuitively. And example 5 will sort of, example 5 is also just, I've had students just ask me about what exactly they are looking for example 5. So I wanted to go through it. Example 5, and again, I'll talk about perpendicular in class on Wednesday, but example 5, find an equation where the line is parallel to y is equal to 2x. So what they're doing, I'll emphasize this in the color black, so they give us the equation of this line already. Everything about this line is already known, and this line in black, and it's called y is equal to 2x. What they want to know, I'll emphasize this in blue, is, all right, cool, you have an equation for that one? Awesome, I want an equation for this parallel line over here. And even more so helpful, I'll tell you a point on it. Okay, so, and naturally, let's go ahead and put this in slope-intercept form. So if anything, let's go ahead and set up the template. This is going to be y is equal to mx plus b. So naturally, we need the slope and the y-intercept. If anything, I think the y-intercept is pretty easy to figure out. With that, remember, we're looking for the blue line. The black line is just supportive. Since they give us the graph, well, we can figure out the y-intercept just by looking at it. In fact, I just emphasized it in red. So the y-intercept seems to be 4, the y value. So if anything, we have the y-intercept. We already have half of this problem done. So finally, we just need the slope. Now you can use rise over run. or you can use something even easier. So you could look at this and figure out rise over run. That's perfectly fine. Let's go ahead and emphasize what it means to be parallel, because that's why they gave us this other line here, this line that I overlaid in black. What is the slope of that line? It's 2, because this is actually in slope-intercept form. It's technically 2x plus 0. So this is in slope-intercept form. So for this line, the slope is 2. And if we have a parallel line, then naturally that slope has to be 2. So by virtue of this slope being 2, that means this slope, not y. Let me hurry up. Yeah, so that slope is 2. I think you see where I'm going with this. Slope is 2, and now we have the slope x plus 4, and then that's it. Yeah, so I'm definitely out of time. You know the drill. In-class people, do you have any questions about anything? If not, this homework will be due Thursday. I will finish this section on Wednesday. So start doing the problems that are accessible. So that way it's not as much of an uphill battle when Thursday comes around and you're doing it at midnight, like I would probably do. Okay, so Google Meets, if you don't have any questions, you're free to go for the day.